How many numbers are there? Well, you can count forever. 1, 2, 3, and the list just never ends. They never stop. That's infinity. And we tend to treat it as a single thing, the end of the line, the biggest there is. But here's a question almost nobody thinks to ask. Is there only one infinity? Or could some infinities actually be bigger than others? By the end of this video, you'll be able to prove the answer yourself. Here's an analogy that I like to use called Hilbert's Hotel. To get our hands on an infinity, picture a hotel, but not any hotel, one with infinitely many rooms. Room 1, room 2, room 3, on and on forever. And tonight, every single room is full. Then, a new guest walks in. In a normal hotel, that's it, no vacancies. But watch what this hotel can do. Let's assume that there's a manager, and they ask every guest to move up one room. The guest in room 1 goes to room 2, the guest in room 2 goes to room 3, room N to room N plus 1, everyone starts a room, so and so. And room 1 is now empty. The new guest that just came in checks in, and it gets stranger. Suppose infinitely many new guests arrive. No problem. Send each current guest from room N to room 2N. Now every even room is taken, and every odd room is free. Infinitely many openings, infinity plus infinity is still the same infinity. When are two infinities the same size? We can't count them, so here's the test. Two collections are the same size if you compare them up perfectly, 1 to 1 with nothing left over. Take the counting numbers and the even numbers. Pair 1 with 2, 2 with 4, 3 with 6. Every natural matches exactly 1 even, forever, none left over. So, impossibly, there are just as many even numbers as numbers in total. The same trick works for integers, negatives and all, and remarkably, even for every fraction. They can all be lined up and paired with 1, 2, 3. We call an infinity like this countable, and so far, every infinity we've met is the same one. So maybe all infinities are equal after all. That's exactly what everyone assumed, until Cantor. Picture every real number between 0 and 1 written out as an endless decimal. And just suppose, you could list them all. Every single one in order with none missing. Now follow the diagonal. The first digit of the first number, the second digit of the second, the third of the third, on down the list. And build a brand new number from it with one rule. Change every digit on that diagonal. If you see a 1, write a 2, and so on, all the way down. Now ask, is this new number anywhere in the list? It can't be the first number, they differ in the first digit. It can't be the second, they differ in the second. It differs from the nth number in the nth place, so it matches no row anywhere. But we assumed the list contained every real number, and we just built one it missed. The only way out is that the assumption was false. The real numbers simply cannot be listed. So picture the two side by side. You have the counting numbers, separate countable dots you could tick off one at a time. Then you have the real numbers, a solid, unbroken continuum, too dense to ever line up. There are strictly more real numbers than counting numbers, not the same infinity made larger, I mean a genuinely provable bigger infinity. And once there are two sizes of infinity, there is no reason to stop at 2. Take any infinity, form the collection of all its possible subsets. That new collection is always strictly bigger. If you do it again and again and again, you will find yourself an endless tower of infinities, each one dwarfing the last. There's no largest infinity, there can't be. So here's where we've arrived. Infinity was never a single destination. It's an endless ladder of sizes climbing forever. And some infinities really are bigger than others, and there's no biggest one. Let's just sit with what just happened. With one diagonal, a single argument you could follow, we proved there are different sizes of infinity, and infinitely many of them. But it leaves one haunting question. Between the counting numbers and the reals, is there any infinity in between? It's called the continuum hypothesis, and the answer is the strangest in all of mathematics. It can neither be proved nor disproved from the standard rules of maths. Not because we're clever enough, but is provably undecidable. This hints at something deeper and even more unsettling. That maths itself, it has limits. So next time, the truths that can never be proven.